Good morning. I'm Jonathan Lowe. I'm a senior computational scientist at ACRC for over 5 years now. I'm also responsible for managing our experimental and exploratory systems. So this is why I'm talking about experiences with powering Power 9. Okay, so first of all, what is ACRC? We are the A-Star Computational Resource Center, and we've made it our mission to meet the high-performance computational needs of the A-Star research community. So that also includes their collaborators, which could include people from AWS. So we manage the HPC resources. We're located at Connexus level 17 at Fusionopolis 1. So our claim to fame used to be that we have the highest data center in Southeast Asia, but I'm not sure that's true anymore. And in February 2016, we signed up as an associate academic member to the OpenPOWER Foundation. So this is what we have. Our first hardware was the Firestone servers with 20 cores per node, 256 gigs of memory, and K80 GPUs. They've gone through several upgrades. We've doubled the memory capacity, and you'll see later why. We've changed over to Volta V100 GPUs, and we've upgraded the Ethernet from 10G to 40G. We've added in a one new server for development and login. This is the Stratton server made by Supermicro, and our recent hardware is an IBM Power 9, codenamed Witherspoon. It's the air-cooled version, which you can see pictured here. You can see one of the CPUs because one of the heatsinks is removed, and this gives us about 40 cores in total to play with. So we understood that one of the unique selling points of the Power 8 hardware was its high sustained memory bandwidth. So I presented this slide in one of the workshops in 2016, and I managed to get a few stunned faces in the audience. The yellow bar being the Power 8 server. So we were getting roughly half what it should be. It turned out that we only, if you look at the block diagram, this is taken from the IBM Red Books. It turns out that we only had half the number of buffer cache chips in use. So each memory controller is linked up to 2, but our installation only had 1 attached. So that's the reason why for the performance. So when we finally got around to upgrading the system, we managed to. So this doubled the bandwidth we managed to measure. I've also thrown in the scores we managed to get for the Power 9 system. So on average 250 gigabytes per second. And we also have an AMD EPIC server that we have in our lab as well. So quite relatively competitive.
So the Power 9 is very
Power 9 is this blue bar here.
Yeah, AC922.
AC922.
Okay,
yeah.
good.
Another unique selling point is the high-speed link between the CPU and the GPU. So on our model, we have three NV links compared to the nodes on the Summit supercomputer, which have only two. That's because on the Summit node, one Power 9 CPU has to balance out to 3 GPUs, whereas in the air-cooled version, it's one Power 9 CPU to 2 GPUs. So that's why 3 links instead of 2. So we can test this for ourselves by running the sample bandwidth test from the CUDA SDK. So on Power 9, the rate of transfer from host to device manages to measure about 65 gigabytes per second, compared to about 11 for the Power 8, which is over the PCIe bus. Another interesting thing to discover is when you query the memory topology of the system. So if you query how much memory you have available, it's more than the 256 gigs installed, and turns out that the memory on the GPUs is also seen by the operating system as a separate NUMA region. Of course, it makes sense. There's no CPUs attached because it's memory on the GPU. So that was an interesting thing to see. So let's look at NAMD, which is a scalable molecular dynamics code. You can run it on both CPU and GPU for performance comparison. It's one of the top 5 codes used on our HPC resources, and there are comparable results online from the NAMD webpage itself and this blog from a vendor in the US that I keep track of. So I took the satellite tobacco mosaic virus benchmark using NAMD version 2.13, and I managed to generate this table of results. So low is better. So how many days for a nanosecond of simulation? So this top half is results I've done on the Power 8, and this one on the Power 9. So it's no surprise that the Power 9 improves over the Power 8. So this is just using the CPUs. But if you look carefully, what strikes you is even using one GPU would beat any score from the CPUs. If you're just looking at the node at the server level. So I'm using 20 works. So I straight away use the same number of cores, and also explore to see whether loading more than one per core would help, because they run SMT, or some version of training. So the best score I could get was 0.16. I came close to not getting these results in time, because whenever I tried to run it on the Power 9 with the GPUs, it was always segfaulting. So thankfully, updating the NVIDIA driver managed to solve that, and it managed to work. Testing Docker and TensorFlow to have a look at the performance amongst the GPUs we have. So I took the the IBM Power AI container and ran it on both Power 8 Power 9 systems. So here you can see the number of images per second you can process using some synthetic convolutional neural network benchmark. So from K80s to V100s and the V100s on the Power 9. So these embedding GPUs managed to pull out further a bit because the embedding GPUs on the Power 9 can consume up to 300 watts compared to 250 for the PCIe version. Moving to a genomics test case, we saw this white paper from IBM about running the G80K toolset on Power 8, and so they were able to show you can complete processing of data sets down to hours instead of days. So we said to them, well, if you can do that, can you do that on our system? So we invited Yinghe, Kathy, and Gilbert to onto our system to validate performance. So initially they couldn't match what they got on their own system because of the memory bandwidth performance mismatch that I showed earlier. So actually, while we were doing this, what we ended up doing was powering down one server and taking all the memory modules from that server and putting it into another. So we fixed the memory bandwidth issue. Another difference that may is for our setup, we were using a BGFS parallel file system instead of GPFS that they were using. So this is the result that they did on their own system at Poughkeepsie in the US, about 6 hours, 16 minutes to complete the process. And they did it on our system, slightly, just about 12 minutes longer. And my colleague ran the same thing and managed to get 6 hours and 24. And he also contributed some usability feedback on the G80K script. So that was appreciated. So that was G80K on Power 8. Our most recent test is using PowerBricks on the Power 9 system. So PowerBricks is a native reimplementation of the G80K algorithms on GPUs. And Gilbert and Ruzu Chen from IBM introduced us to their technical lead, Ankit Segia, and we invited him onto our system to install it and give it a test run. So we set up the Singularity container framework for him, and there was some NVIDIA bug fixing which was sorted out. So after he installed it and tested it, we tested it ourselves. So using the original G80K script on the Power 8 system with our own data set, this completed in about 4.5 hours. But using PowerBricks, which makes use of the GPUs, this all goes down to 45 minutes. So, and this was only with 2 GPUs, so they claimed that it scales very well with more GPUs. So if we had a full system before, I imagine it'll be around 20.
Is that comparable accuracy?
From what I've heard, it's the correctness and accuracy is pretty impressive. Yeah. Okay, so I'll finish off with some final thoughts. First of all, I'm very impressed that with IBM and with the hardware, it's open in such that the system firmware BMC, you can actually see the source code from these GitHub repositories. So unlike other systems, you can actually download the CPU motherboard and boot firmware, and if you can compile it and run it yourself. The second point, especially with Summit and Sierra up and running, we hope that the software ecosystem will more or less reach parity with the x86 ecosystem. There's still a few programs that we come across with compilation problems or low performance because there's not yet optimized routines for POWER hardware. And finally, we continue to watch what future computing solutions there are from the OpenPOWER collaborative efforts. There's the example from OpenCAPI, which we've not yet evaluated, but interested to see what that could mean for our users, and we'll continue to watch what emerges from the OpenPOWER Foundation. Okay, that's the end.